Okay, hi. Today I will talk about TTF exploitation and how, not too much about how you find the bug, but more likely about how the bug, what we need to exploit this bug, and some techniques, how to get kernel execution, not just system calculator. This is basically outline. We're starting with quick what is TTF. How's the story? But we start finding the bugs in TTF and why we do it, and some difference between the previous public TTF research and ours, especially exploitation. And then we turn to how to exploit in kernel, how to get kernel execution, and how to bypass some mitigations already implemented, and some of them are not implemented yet, but anyway, good to play with it. So, but at the beginning we start who we are. We are a Keen team based in China, mainly Shanghai. And so what we are doing, we're doing security research and well, like challenges, competitions, and security. And that's why we join competition like Pontoon, where we pop some system calcs and also actively contributing to key community, for example, the ping pong route. And we're joining also cooperation with Project Zero, and we share some different research in form of blogs, code, tools, or conferences. We produce out of CVs and get out with some techniques. And we was previously presenting also at some other conferences about some kernel issues, about some design and how to bypass some mitigations, but it was mainly in theory. Now we will show how to do it in practice. So we can start with what TTF is. What's TTF? I put from Wikipedia, and basically it's some system for showing the formats. But for me, I was more focusing on how to exploit it, how to execute those bugs, and for me it was most important some short explanation, and that it's a really cool tool which you can use to arbitrarily read or write kernel by virtual machine instructions, or you can use its feature that somehow it can corrupt additional memory, additional structures and memory around your TTF block, and it can in fact lead to the same arbitrary read or write. And that's enough for us to play with. But I think it was too lazy, and when you want to do more research on TTF and have more background, you can read these materials, but I hope that you are a bit familiar with it. And for exploitation, as I said, it's most important that you can with this TTF, you can achieve some read or write in some good conditions. And so about us and TTF, we started playing with TTF because of Pontoon, and my colleague Lou was responsible for TTF fuzzing, and he built some novel fuzzer and some new idea, and let fuzzer run for about 3 weeks at the beginning, and we found all the bugs, and at least 3 of them was exploitable. But unfortunately, I have not much time to play with it, and so I started to play with it, I think 3 weeks before Pontoon. So it was, and when I started, I realized that most of them was fixed in Patch Tuesday, one month before, and it was a great job for Microsoft. So that it was not so pleasant information for us, but we found at least 2 vulnerabilities what was not patched, and we can use it. But it was quite challenging. And currently now we have some more bugs about TTF, but it's in our to-do list in the near future. And the difference between our TTF bugs and public research about TTF was that in previous research it was abused TTF to use virtual machine instructions to get kernel code execution or to exploit it. in our bug, it was kind of pity that it was back in building TTF block with the state of the virtual machine, and it was you need let's say few instruction, exactly 4 bytes to trigger this bug. But after it, you cannot, and it's not a way how you can somehow cooperate with this bug. It just triggers some overflow, and that's it. And that's what we start. And at the beginning, we got some crashes. And you first thing you will need when you want to exploit TTF is you will need to find a way how to parse the TTF formats. And for this is some good tools available. I recommend the TTX font tools for Python. And also you need, in fact, I use, for example, FileManager and some plugins to go inside TTX and parse the information from TTF in human readable and really quick way. And you can see all of tables, all of properties in TTF and really quick. And you will also need read documentation about instructions about the formats, this kind of stuff. And two ends that you will need to minimize this TTF because when you build some TTF files, you can have a lot of unnecessary instructions, a lot of unnecessary the tables and some big properties. You want to minimize that file and kick out as many instructions glyphs as you can. And then you can do, and for that you need to know about the format, and you probably will need to buy to build some own tools for it. And you end with some minimalist file when you can trigger the bug, and then you can it's really easier to get into the root of problems. And as for one of our TTF bug, it was we got the root cause, but it was that we are able to trigger the bug, and then it will be consecutive overflowing to a lot of pages, but it's the kernel. And that means that you when touch a lot of pages which are not mapped in kernel, it will panic. So it can be a problem. And in kernel, when you touch a lot of pages, it can be a really big deal because you are not supposed to have a lot of control from user mode into kernel. And the worst thing is that we was not able to interact from, when we triggered the bug, we was not able to interact from this TTF anymore. And any other option how to lead this bug. But okay, we go to it and we just kind of look at it properly and try to figure out how to avoid the panic when it comes to this overflowing out of pages. So at the beginning, you can see that in the Windows, you have introducing, for example, 64-bit platform, and we have introducing a lot of gaps in 64-bit address space. But these gaps are only when it comes to, it's only introduced between the sessions. And you have a lot of, between the pools, and you have a lot of pools. But fortunately for us, we was playing with TTF, its own session space. And that means that, for example, in 64-bit, you have, because of the gaps, it's really inefficient to use heap spray, to pool spray. But when it comes to, okay, you know that it's a special pool, pool spraying in this pool is still effective. And you can use it in that way. But for it, you need to find very secure objects from which you are flowing, on which is pool. And in our case, it was session pool. Okay, so we want to look at more about it, and we set some conditional breakpoint on our session pool. And first guess was we would like to go into the big pools, because in the big pools, when you have in the big pools, it's probably not so many randomizations and not so many mitigations in pool manager introduced. So we end up with this kind of informations, and we can look closely and back create DAB, and we look at the IDA, and we check, okay, it's a lot of candidates which are allocating the big pool memory, and we choose the bitmap. And bitmap is a very good candidate, because when you look at the documentation and the MSDN, we see that when you create the bitmap, you can provide us height and width. Basically, you can control the size of the allocated block, and you can allocate it from the user mode directly. So that is very good because then we can choose, okay, it will be a really big size, so it will be stored in the big allocations, and at the same time it will be in session pool, as is our TTF. And big pools really have good features. It's, let's say, not features from the security point of view, because when it comes to randomization, it's not applied to big pools. At least I don't do that algorithm, but if they're introduced randomization, it's really bad. And that means that you can make pool layout, and you can make holes inside, and you can prepare the space for your TTF, and will be later loaded. And as I said, the spraying in some session pool, in some pool, it's still really effective. It's not effective through all the virtual other space, but in the particular pool, it's really effective. And what does it mean? When you know the base of the pool, you can also hardcode. We don't use it, but you can. And also when you do basically invoke the kmalloc or xallocate pool or x3 pool from the user modes indirectly, it's a really cool feature. And that means you can handle the wild overflow. So it means that by design, you have a really good feature that you can do pool layout, and that means that your wild overflow from the TTF will not crash system anymore so easily, because you can spring, let's say, some bitmaps after TTF, then introduce this trigger this back, and we'll just touch these bitmaps. And when you don't touch these bitmaps, it will not panic. And the main feature, why it's possible, it's because even you have 64 bits address space, it does not introduce some page no access between. Because, for example, I was talking about overflow on confidence, and when you use 64 bits in big address space, bigger than physical address space, then you can, probably it's not so efficient, but you can introduce the page no access after some allocations, and when you try to overflow, it will just panic. Maybe it's waste of space, but in 64 bits, I don't think so, and can be really effective and can basically kill these overflows. But it's not implemented, and you can. So I think the overflows is one of the best choices when you want to exploit something, because race condition or other kind of bug you can convert to buffer overflow, and to buffer overflow you can have some techniques, which can be really useful. But when it comes to this particular TTF bug, we have problems. I cannot go deep into details because it's still not fixed yet, but I can say that, okay, we're overflowing from the TTF, but we are not able to precise control the bytes. So that means it's overflowing to some lot of pages, but in these pages are doing mathematical calculations, and some condition is met, then the bytes changed. And for this, you need to, because you want to something change on the purpose that you want to, for example, the boost size. So you want to know that, okay, in this at this offset you want to change and make size bigger. And for these kind of things, you can help with, for example, some SAS solvers, because it can help you that, okay, we have some condition we have to meet to modify the memory, and in addition, we need to satisfy some content of this memory that will be calculated, and somehow semi-control the output which will be written to. That, for example, that we want to boost size to some bigger. So you want to, its size, for example, is 5, and we want to boost it to 10. But for this, to write it there 10, we want to make some calculations. And as I said, for this can be useful some SAS solver based on your contraflow graph and the conditions and the exact problem. So it's kind of getting complicated with this bug, because you go, when you want to patch something in that pool with overflow, you need meet some conditions. You might satisfy some mathematical calculations that you can control at least semi-watts. It was not precise control, but you can, for example, say that the highest byte will be 1 or something like this one. And for that, you have to control the memory after TTF. So that means you have to have absolute control about that memory followed after, which can be a problem because you are in user mode, but the memory resides in kernel mode. But it's not exactly true that it's a problem, because you can find really nice methods, especially for this bitmap. And these really good methods are, for example, the set bitmap bits and get bitmap bits. And in fact, it means that you are able to read or write to kernel exactly data what you wish. So that means you can have in the kernel, in the user mode, the same data as will be in kernel. And that's a really cool feature, because now you can exactly control the bytes after TTF. And to say more about this good structure, it's very good candidate, because you have they said you have size in the header, and you have also some pointer to buffer. And except to this, you can fully control it from the user mode. You can allocate it or free it in kernel from user mode by your will, by create bitmap or delegate object. And you can also set or read the byte from that memory also by some user mode APIs. So in fact, you have full control about that piece of memory in kernel. And then you're able to somehow alter the height or width for the size of the bitmap, you can win. And then the good feature is that the data, the header of this bitmap, is in plain state. So that means that you have in plain state, you have size, you have pointer to buffer, you have pointer to lock. And that's really cool because of some the features. Because when you, from the user mode, when you can expect that, okay, in this memory I can control data and I can read the plain state of the header, it's really good consequences for you, because you can really easy to boost size, because you know that the size you control and you know which are the size, and it's not encrypted, so you can change it. You can boost the size very easily, or you can change the pointer to buffers, or you can, for example, in our TTF, we have to use the header to alter the second bitmap header, and for that was very good that we can expect what will be in the header, because it's not encrypted, it's plain state, and really you can use it. And so how we do is that it's a simplified scenario that we allocate some bitmap after, let's say it will be after TTF, and we want to alter the size. But for this, when we want to alter the size, we coincidentally also have to write to log, and log is some kernel buffer, some kernel pointer. And when you want to access to this bitmap, to read or write to this bitmap, you need get successful access also to the log. So for this, you need to allocate, let's say, the second bitmap and spray the rest of the memory. And that allows you to successfully change the size. And with this, and the log will be points later to far away, but the sample which you already sprayed. So the access to log will be successful, and now you can use set or get bitmaps bits. And what does it mean for you? That it means that even you corrupt the first bitmap, you corrupt it just partially, that you boost the size, but just a little bit. But for this, you can use the functions on this first bitmap to alter the second bitmap header and patch the size to, say, -1, which means that you can read or write to all kernel memory on your wheel. And in our case, we use the troubles because, as I said, that we was not able to directly change the properties of the first bitmap header. So we need to insert the third map at the first place, and we need to use this header to alter this bitmap header. And with this, finally, we can alter the third bitmap and achieve full kernel input-output. And this read and write to kernel is really powerful. And to wrap up what we already have, we started with some valid overflow, and we have, let's say, we can achieve some semi-controller to write with this overflowing bytes. But we can also control the kernel memory, all the bytes, let's say almost all the bytes. And then we achieve some recursive technique also to full writes or read to kernel memory. And that's really powerful, but what you can do now, what do you want to do now? Now we want to go to kernel. For example, the patch, the token, and public system calc. But for this, you now facing some kernel security, some mitigations introducing by Microsoft, and somehow it's really good. You have some 64 bits of the space, not some security feature, but in fact it's good cooperate. We found security features. And second thing is, for example, we have kernel address space randomization, and you have also, by default, when you allocate memory, it's non-executable. It's also a really good feature. And you have some supervisor mode access and execute prevention. Access mode prevention is not implemented yet, but hopefully will be soon. But we also, when we play with this exploitation, we also take in consideration also this one, and also some counterflow integrity. In fact, the counterflow graph guard. And at the first, what is the kernel space address randomization? That means that when you load some module to kernel, it will be at some random places. It will basically will be random base, which will be stored these modules, and the same applies for different pools. So that means between the different pools will be some page no access. So that means you are really in trouble even when you should be really in trouble even when you have full reads and write ability to kernel, because now you have a lot of gaps in kernel, and at the same time it's randomized. So that means even if you have read and write to kernel, you are really afraid to touch anything because it can crash. But in fact, and for this you can overcome this in general by some info leak bug. It should be correct way, but because it introduced the let's say it's harder to exploit it because you need second bug just for leaking some information about the memory layout. But in fact, it's when you have read and write to kernel memory currently, you can bypass it very easily, these features, because you can use, for example, SIDT or SGDT instructions, and you got leak some pointer to kernel, and which points to another pointer, and you can some recursive reading to figure out where is the module basis. So you bypass KSLR, and you are not afraid of the gaps with page no access anymore. Or you can use some other old, very known and nice technique. And that technique was introduced in 2011. And when I use it, it was because in second TTF bug, I do it for Adobe PDF reader, and it was in 32 bits. And I was not able to use this technique because when I use the SGDT or SIDT instruction, it returns me 0. Okay, because it was not leaking pointer to kernel anymore. So, but I was lazy to find some new technique when I have implemented also this one, and I like it. So I was looking for some other feature how to do it in really fast, because I have some time pressure. And I remember that in the past it was introduced some really good article about some kernel exploitation, and it was by Tremont in 2011. But I was sure that it's already fixed, but in fact it isn't fixed. And this is a mighty feature that geshard info. And when you look at this, you leak the pointers from the kernel directly from the user mode, because only thing you need is read the symbol, public symbol from the user 32 DLL, and then you can read the pointers from the kernel. And really in leaking the base of the session pool is really a problem. Because as I said previously, when in this era, when you have 64-bit data space and kernel address space randomization, you have a lot of gaps. And your main problem is to get some valid pointer. And especially when you get session pool pointers, I think it's early game over. I will show later why. And and at least because of when you link the address to the session pool, you can use the technique to convert your bug to full read-write with the bitmaps as I previously shown. And except that you will link the pointers to the session space, you can read more, and you can find also pointers to eProcess. And that's it, that you can end up with some system calculator, because you have full read-write to kernel, and you link the pointers to eProcess. So what you need is basically just patch some token in your eProcess and pop system calc. It can be good, but not good enough, because we want to go deeper. We want to get some kernel code execution, because I think it's a more serious issue. And to get system kernel mode execution, you need somehow to jump into kernel to your own code. And one of the good candidates is HAL dispatch table, but I want to look at something different. So for example, you have here some function. It's anti-user mode, anti-user message call. And it's I choose it because it has some in this function, it's virtual call. And this virtual call is based on some virtual table. It's a virtual table with some function pointers, which is in read-write that section of Win32k. So in fact, in theory, before we can just overwrite all these pointers, invoke this function, because it's just simple syscall, and you can just execute some code by supervisor privileges. But nowadays you can't, because you have introduced supervisor mode execution prevention. That means that when you introduce syscall, you are in kernel, and when you want to jump to user mode code, it will just panic, because it's not allowed. You can just, with the supervisor privileges, you can just jump in the supervisor mode space. You cannot execute any code from the user mode. And also we play okay. SMAP is not enabled yet on the Windows, but let's say it is. So we have also problems that we want to we execute supervisor mode code, and you want to touch some data in user mode. We cannot, because it resides in user mode. So we have to read just data from the user mode, or some map it from user mode to kernel, and then you can read it. And it's what makes these two mitigations so powerful is also in combination with non-execute flag of the allocations, because that means that you can code is basically their code is data, and the only one difference is that data can be executed, and this non-execute flag make really difference that between the data and code. And so now you already bypass the in this point of view, you already bypass the SMAP with that function set and get bitmap bits, because you can port some your controlled data to kernel, but still you cannot execute it because you have SMAP, and you have also you have SMAP is okay because now your data is a kernel, but you have non-execute flag, and then you can jump to it because it's non-executable memory. And you can play with it because now you have also read-writes to kernel, and you can basically use the page tables, and you can alter the page tables and alter PT entry. It was previously shown by some research. But we want to do it's also when some better protection, some additional protection implemented, for example, like a trust zone that you cannot, even with supervisor codes, is alter to page tables. So it was kind of enforced the SMAP and the SMEP. So, but what we can do on Windows, you have good functions, allocate pool, and you can allocate also execute read-write memory with this. But okay, so we want to use this function directly. And remember that we have full kernel read-write, so we can use some, as I said previously, for example, some rewrite some function pointer and to invoke syscall and jump into this function. And okay, it can allocate memory, but you have two problems. You need to this allocate pool and provide some valid arguments. First is you need to provide good flags, And this flex should be read, write, and executable. And second thing, you need the leak the address which will be allocated. Because, okay, you can call some syscall, it will, let's say, redirect to X-allocate pool, and it allocates in memory, but you don't know where the memory is because you don't leak the pointer back. It can be your problem. And you should also provide that it will be really executable page. But for this, you can use a little bit tricking. Because anti-user message code and anti-user message call I use on purpose because it can be at first really easily to call from the user mode. Second thing is that in the middle it contains, as I previously said, the virtual call. And the third thing is that from, the output from the virtual call is directly copied as a return to user mode. So that means when you rewrite some function here in this virtual table to X-allocate pool, you are able to leak the allocate memory back to you. But still can be problem. Okay, now you can allocate memory, you can leak that pointer, but you need to be also executable read and write. And for this, you need to provide those flags. And as you can see that second argument is okay. Second argument is provided from user mode, but first argument is handle. When you call the syscall, the first argument is handle to the window. And later on is called validate HVND procedure, which translates this handle to kernel mode pointer. And this kernel mode pointer is provided as the first argument to this virtual call. And that means when you are able to get some handle, which will be after translation, translated to kernel pointer, which can be interpreted when it looks as a flag, that it's flag with read, write, and execute, you can win. But how to achieve it can be a little bit tricky, but in fact it isn't so tricky, because only thing what you need to do is in the right is get rev window handle, which you basically create a lot of windows, and for each window you call this enter message call, and you want to you read the handle, because you can use in this function you can run the trick. You can provide not just at first you will not rewrite with X-allocate pool pointer, but you will rewrite with some other function which returns you the first argument. So that means when you provide here some handle of the window, it will be translated to kernel mode pointer, and with this virtual call, this pointer will be leaked back to you. So that means that here, when you allocate the window and you provide it to enter user message call, you will leak the address of this window in the kernel. And then you can check if when you can look at this flag, if it's executable and writable. And if it is, then it's our handle what we need. And with this handle, you can allocate, you can change the point, you can change on the pointer, function pointer to points to X-allocate pool, and you can allocate with this handle the size you want. And this memory will be read by the executable with size you want, and you got this pointer back to you. And as I said, you have read-write memory, which you use already for rewriting these pointers, and you can write to this part of memory your control data, which you can later jump to the data. And really cool, but we want to play also with on the feature, because when you some counterflow integrity, let's say it's counterflow guard, which means that you cannot jump, okay, you have some virtual call, let's say it's implemented the kernel. For now it isn't so well, but let's say fully implemented the kernel, it's working. And so that means that when you invoking the kernel some virtual call, it will be checked before if this address of this virtual call is in some register. It's a valid function, and if it can be used in some virtual call. And if it's not, it will panic. If it's yes, then it's okay. But in fact, this counterflow guard, it's only covers some idea of the ROP, but ROP is kind of old. And but I admit it's kind of handle this issue, this ROP issue, kind of effective to some extent at the beginning. But when you look at different scope, that's you can exploit some these virtual calls with just also with some valid functions, but we provide some amount of function that is supposed to be called. That means you can somehow change the state of your machine. And for example, in the kernel, when you have, free write to kernel, you can call, for example, this virtual call many times. You can override this pointer many times at some amount of function, and so you can do step by step to make somehow to make state you want, to leak some pointers, to set some memory. It will be not like, let's say, some ROP that, okay, you make some ROP chain and then just invoke this call and it will trigger all ROP chain and you will go to some kernel code execution. But with this, it will be more steps that you will change one pointer, it will do something for you, and then you will change it again, you will call in the kernel again, and we will change the context again, and you will repeat a lot of times, and you change the logic. And at the end of this, you can hopefully get some kernel code execution. It will be somehow complicated, and you need to find some registered functions, which is registered, for example, in this bitmap. For example, that's in our checking, getting allocated the read-write executable pool. We use exactly this kind of function-driven attack that we provide just valid function pointers. But I admit that I use the really easy functions that do directly what I want, so it was really easy. And most likely that those functions will be not registered in valid functions. But it's okay. That means for me that it will be next time it will be more harder. That I need to find more functions to do it more step by step. It will be not just directly, for example, deleting memory or just allocating memory on the first step. But I can somehow abuse the logic because control flow guard is not exactly about the control flow integrity. It just care, okay, you have from virtual calls you need to have just call some registered functions. It's not about, for example, have some object, and this object have only for this object have some valid calls. It's some, let's say, some global bitmap with some other functions there, and that allows you from the different object call some different functions which is not supposed to be called from this object. And second thing is that at the last step, okay, for example, now we achieve full kernel read-write. We allocate our memory, which are read-write executable, and we are able to pass the data to that memory. But the final step will be jump to this memory. And for sure, when we allocate our piece of memory, even it's executable, and we get our code there, this function which you want to call is not in this CFG bitmap. So you will need somehow to jump into it. And let's say CFG is implemented, but now we have the other problem with design is that we have one stack which is mixed. On this stack is mixed data and also mixed the control flow pointers, return addresses. And when you are able to once to find the stack address and to change this return address, then you are over. I think for this solution I present also in Syscan. And it was not my idea, it's I think not novel, but it really helps when you have two different stacks. One stack for data and one stack for control flow. That means, for example, for control flow, you are able to alter it with some subset of instructions. That means in the future, even when you have kernel read-write, you're not able to alter the kernel stack with kernel control flow stack because it will panic. Because, for example, to this control flow stack, you can add value only when you call something jump or this one. You are not able to alter the stack with some mo or pop instruction, for example. So it can solve the issue, but for now you have mixed the stack with data and control flow informations, and you can do stack hooking. So for example, we have kernel read-write primitive, let's say write primitive, and we somehow delete the kernel thread. Is no problem when you have full read-write. And we now have also our kernel image into kernel. So what we do is basically call this write function, call this write primitive, and this write primitive, we just rewrite the return address, which will be returned after this call. So that means it will return to our code. That means there will be no additional checks performed if it's valid function or not, because you hook directly the stack, and in current design you can do it. And so in the end, we end up with system calc and also with kernel driver. As you can see at the bottom, we have some print from our kernel driver. Because we achieved the kernel read-write, we achieved the allocating the executable memory, we loaded our data and we jump there, and it's over. And let's say that popping calcs is can be doing. It's not so hard in these operating systems in general. Because, for example, in Windows, we have some really good technique for overflows, and you can use it in generic way. And only thing what you need to implement is some details about your vulnerability, and the technique can be used. And most important thing is that is there around the issue that you can basically with current let's say with current Windows, you can achieve the kernel code execution. We just write 1 byte. We just or 0 to 1, and it's over. But you have to control where to write, but you need just this one, and you can pull all the kernel, because you can link the session-based address, and you can use the technique alter the bitmap, and you can use it. So it's only this thing is necessary to own the kernel. And when we look at the aftermath, that's, for example, this our TTF bugs, we report the pwn to own, and now we can present all the details. We can present details of the bug because it's not fixed yet. Before this I tested, and it's perfectly work. And I understand that's really hard to fix that vulnerabilities in kernel, especially about the TTFs. But in general, fixing the kernel can be a really long process. But when we look at it in different scenario, that for us, we let fuzzer about 3 weeks run, and we got 3 bugs. Implementation of this fuzzer was, let's say, less than a month. And we do it for security and for fun. We collaborate on the fixing and we report it. But the other guys are doing much more research about ETF than us, do this research before us, and do it probably also now. And as you can see, that for us it was about, let's say, 2 months to find those bugs, and now it's more than 3 months. It's not fixed, so it's really possible that also these guys have this bug. I don't know, maybe not this, but they have some other bugs. And I think this kind of bugs should be early fixed as soon as possible. And as I said, exploiting those kind of bugs are not so hard, even if they are in kernel. And why it's not so hard? Because in current OS design, current operating system design is really old. So it have when it was designed, it was not too much care about the security stuff. And now it's by design some broken, even some new, introduce some mitigations and some hardenings. It's by design it's broke. It doesn't cooperate pretty well. So I hope in the future it will be designed maybe from the scratch, maybe not, but I hope it will be really some major redesign of these systems. And the other thing is that known security issues like leaking some kernel addresses, for example, the session pool is public, and it's public for 4 years, and it's still, you can use it. And that's a big deal. And ending the presentation, I want to invite you for our events. It's some event for the geeks. You can pawn smart devices. We organize it in Peking. It will be on 24 October, and it's open. So when you want to present some research, to pawn some device, just send us your submission, and if you think it's cool, you can go inside. You can pawn the smart device, you can pawn the cars, microwave, smartwatches. What do you think is cool? Really appreciate it, and this will be Rainbow Strip. So this time for questions. And by the way, we are hiring. So if you have any questions about this presentation, just ask me now or later. What do you prefer? Okay, thank you very much.